Hello.
Hello, Pavel. How are you?
Hello. Yeah, hi, Viv. How are you?
Good to see you.
Okay, so let's check that everything is working.
Yeah, please go ahead.
Okay, so how is the sound on your side?
Sound is fine.
Okay, I'm doing this because, to be honest, this is my second online talk.
Oh, okay.
Yes, I'm very conservative, and I try to give talks only in person. So this is exception.
We are honored to be the second institute to receive your online seminar.
Yeah. Yes. So let me check how to share my screen. So do you want me to share my screen with presentation? Is it the way to go?
Absolutely, yes. So it's a good time to check it.
Right. Where is the... So where is the share screen? Oh, okay. So here it is. Share screen.
Yeah, share screen is the green arrow at the bottom.
The green button.
And then you can choose the specific window for the PowerPoint or whatever you're using.
There is also whiteboard option.
Yeah, there's a whiteboard.
Yeah. Okay, so here is the screen shared. So what do you see now?
Oh, so you share the entire screen.
Yeah, okay,
You can do that if you like, but I think it's usually more convenient to share just your presentation specifically. It's usually more streamlined. But so if you want to try that, you can stop sharing and then start.
Yeah, let me
choose the specific window.
So I have this
you
window.
would first open it. You have it open?
Yeah. I opened it.
So now share and choose that specific window if you can see it in the list of windows shown graphically.
Zoom. Okay, so it's again share screen. Okay, here it is. Right. Okay, that's convenient. I used something else for the previous talk.
Okay.
So what do you see now? I think you see...
I see it's a PDF presentation, yes?
Yeah.
Okay, I see it very well.
Let
me you can minimize the left.
Let me make it all screen. Hold on. Show you full screen mode. So how can I know?
We go. So we're very happy to have Pavel Berloff with us today. Pavel did his PhD at Florida State University and then postdoc at UCLA with Jim McWilliams, who was also my PhD advisor. So we have some common history. And then he moved to Woods Hole and to Cambridge, Department of Mathematics after that. And for the last 15 years, he's been in Imperial College. And he has a very wide range of interests, including geophysical fluid dynamics in a pretty broad sense, its connections to scientific computing, dynamical systems, climate, of course, and I think some and turbulence, eddy parameterization, and that's partially related to what he'll talk to us today about. So please take it away, Pavel.
Okay, thank you. Thank you very much for inviting me, giving me opportunity. I have to honestly admit that this is my second online talk, so I'm not quite well. I'm still learning things. how to do good online talks. Okay, now about the subject. This was collaborative project between UK and USA groups, jointly funded by the NSF and UK research councils. Mike Hake is a postdoc now in the UK. Loalin San is postdoc in France, and Yuyan Klu is postdoc in the States. So all younger people involved have established themselves quite well and continuing on the academic research track. And Jim McWilliams was involved at the later stage, and I will explain why. It was really good to have him on board on this project. One slide on very broad context and background. So the whole story is motivated by mesoscale oceanic eddies, which is synoptic turbulence in the ocean. This is a snapshot of sea surface height, and blue and red dips over here are manifestations of mesoscale eddies on the surface. The point is that these eddies are everywhere, and they're very important for establishing ocean circulation. They influence climate. So they have to be either directly resolved by high-resolution models, and this is super expensive computationally, or dealt with indirectly by eddy parameterizations. So this, my talk, is within the context of eddy parameterizations. Eddy parameterizations are mathematical models for eddy effects, basically, turbulence closures. And this, my talk, falls within the broadest category of eddy parameterizations, which are all based on the idea of turbulent diffusion, which is 100+ years old, starting by a famous paper by Taylor in 1921. So try to think within this context, eddies and very diffusive parameterizations. Now, one slide is a crash course on basics of eddy diffusion. So the eddy diffusion is based on even more fundamental statement, which is flux gradient relation. Flux gradient relation is really foundation for the whole idea, not the diffusion itself. Flux gradient relation tells us the following. Suppose we have turbulence denoted in my talk by bars, something large scale. No, sorry. Bars denote large scales and primes denote turbulence. If we split the flow in bars and primes, there will be turbulent stress terms like this, prime terms. They always come out. If these turbulent stresses can be expressed through large scale gradients, we're in business, because all primes in the governing equation will be replaced by the diffusion term. That's the idea. But this relation involves the magic coefficient K, which sometimes is called diffusion or viscosity. It has different incarnations, different names. We will call it transport coefficient, and we will treat this K in the most complete form, neglecting nothing. So our idea is to consider it completely. So it's such a simple relation. Its consequences are so simple. So how come we're messing up with it for more than 100 years? So this is my list of 7 fundamental problems which are not resolved, and we're still facing them. Let me quickly go through. First, it's a problem of incompleteness, flux gradient relation. Why is this relation local in space and time, for example? Why does it involve gradient and not second derivative? There are many questions like this. So all these questions are about completeness of this statement. Second problem is about coarse graining. How do we separate flow field in bars and primes? There are infinitely many ways to do this. Which one is correct? Third is observational problem, because this statement over here is Eulerian. It's local in space and time. K is local in space and time. But especially in the ocean, most of the observations are Lagrangian. They come from floats and drifters. And Lagrangian estimates are fundamentally non-local in space and time. So there is a gap between two things, Eulerian description and Lagrangian measurement. Next problem is about non-uniqueness. So suppose we estimate K from a tracer, let's say from temperature, for example. And then we do the same thing for salinity in the ocean. Okay, same turbulence, just different tracer fields. Will we end up with the same K? What if we use purely passive tracers, but different combinations? Will we end up with the same K? We really don't know. And there is an issue of non-uniqueness. K can be non-unique. It can depend on the tracer itself. And next in the list is field closure and physical constraining problem. So we may know K from estimates, but we still have to relate K to barred fields, to what is actually resolved. There is also a problem with negative Ks, and it's ill-posedness. If K is negative, then the diffusion operator is negative, and it will blow up in finite time. It will create singularity. That's not going to work. That's a problem. And finally, what do we do if gradient is zero? We can't divide flux by gradient. We can't divide by zero. So K is undefined, but in reality, K can be very spiky. It can have very large values at some points and locations in space. So all these problems are there. That's why the diffusion issue is still alive. There is a lot of science to be done. Now, within the context of my talk, I will consider things, of course, in some simplified way. So I will estimate K diagnostically from eddy resolving ocean model. So the questions about K will be diagnostic. What is exactly there? And our approach will be brute force in the sense that we will neglect nothing in K. And we're the first people, actually, in science who have done this. Because all other scientists, they either neglected something or averaged out something or put some additional constraints on K. For example, having positive eigenvalues or something like this. No one has ever completely considered it. Okay, so the ocean eddy resolving model will be in layers. It will be isopycnal QG. So for each layer, K is 2 by 2 tensor. And we call it transport coefficient because it contains both advective and diffusive eddy effects. Many people do not understand that there are advective effects inside. That's why I'm stressing this. And we will consider K as spatially inhomogeneous, time-dependent, anisotropic. All information will be there. So that's how we will proceed. Now, I'm going to skip this slide, just mentioning that our focus is on eastward jet extensions of western boundary currents. So we're mostly interested in Gulf Stream or Kuroshio regions and mid-latitude basins for many reasons. So the model that will produce maps of K for us is a quasi-jet-strophic PV model. So square basin of the North Atlantic side, flat bottom, beta plane, steady wind forcing, very turbulent solutions, fine grid resolution, Rossby radius is standard. Well, we solve 3-layer QG. Here is a 2-layer description just for brevity. So it's PV conservation law plus some small viscosity for sub-mesoscales, bottom friction, and impulse steady wind. Standard model, double gyre model. That's a snapshot from the model. This is potential vorticity anomaly for the upper layer, random snapshot. Gulf Stream, meanders, eddies, it looks very realistic. It's a decent solution. Then we filter it in space, not in time. Filter by running small box average around. And this left snapshot will fall apart in large scales and eddies. So middle and right panels added together will give me left panel. That's for you just to understand what are the eddy scales that we're talking about. So the filter size become part of the problem, and we vary it and look at its variation. Okay, all fields will be decomposed in the same way. Okay, next slide. I'm still preparing and explaining you the setup of the model. So within this quasi-geostrophic solutions, in them we put tracers. So tracers are passive concentrations. Here are standard equations for them, and they are just advected by velocity field. We put many tracers, tens of them, dozens of them, because we need many tracer pairs. I will explain why. So all these tracers are different by their initial conditions. We put them in different shapes with different gradients so that they are linearly independent from each other. Okay. Then we solve for all these ensembles of tracers on the top of the flow field, decompose everything in bars and primes here by our filter, and substitute this back in the equation. So I put this decomposition back into this equation. Everything can be sorted out. Look, the blue terms contain primes, and all of them, all these blue terms together, we refer to as eddy term. So this is information from eddies, which provides effect on the large scale flow field. This is equation for predicting large scale flow fields. The other way, this is uncommon way of treating eddy term. There is more common but less convenient way, is to take this original equation and just filter it in space, equation itself, not decomposed, but filter equation. So if you do this, and if things are nice, so that filtering commutes with derivatives, in this nice situation, the eddy term is written like this. This blue term is equal to that blue term. Exactly, okay? But the first one is more convenient because we have access to every single term, and every single term has clear physical meaning. Whereas here, everything is lumped together. And plus, we have time derivative explicitly here. Mm-hmm. Anyway, we stick with the first formulation. And then our next goal is to translate this blue term into maps of K-tensor. That's the second goal. How do we do this? So first of all, let me show you that this is divergence of fluxes. This is eddy flux, and this is extra term. Okay. The flux contains three parts, not only stress, but also cross-correlation terms. All of them are important. Divergence of flux is sitting here. So first, what do we do with these extra terms? So we treat these extra terms as divergence of extra fluxes. So this is scalar. It can be written as flux divergence, and this flux can be found under assumption that it's purely divergent. So we find the underlying flux and add it to F, okay? So this is basically absorption of extra thing into the main flux. So from now on, I will forget about these terms, and I will talk only about this upgraded flux. Okay, so we have all the solution. We have flux for each tracer from the ensemble. Ensemble is large. We have this information saved and recorded, and we want to find K. We have flux gradient relation written over here. This is large scale gradient, particular tracer. This is K. Y on isopycnal layers, so K is just 2 by 2. It has 4 unknowns, but F is flux vector. It has 2 entries. So 2 equations for 2 entries for 4 unknowns. That is sufficient. We overcome this problem by considering pairs of tracers. So if we take 2 independent tracers, CP and CQ, and write pair of equations, then we have 4 equations for 4 unknowns of K. This is well posed and solvable problem, and we solve it. If our ensemble has dozen tracers, it's about 100 pairs, because it's easy to calculate how many pairs can be formed. So we have many pairs and many estimates for K. Okay, so we can compare Ks for different pairs, but I'll talk about this later in brief. Anyway, so we have maps of K, okay? And all eddy term, all eddy effect in the equation is replaced by this operator, divergence of this flux written in the K form. all done. What is the K that we obtained? Can we learn any new information from there? And before I tell you plenty of the new information, let me quickly illustrate you so that you have this picture in mind, how things look like. That's a large scale tracer concentration, some random snapshot after some time with initial distribution subtracted so that you can easily see the scales. So these are large scale. The small scales corresponding to this are a lot smaller, C prime. So the combination of these two panels will give the full concentration field, okay? And the eddy term, which is divergence of the flux, is even more noisier. So what we do, we translate this in the diffusion description, and our K is fitted for this F, okay? No information is lost, okay? So our all information is complete. It's on the fine grid, nothing was neglected, right? Now, just few side remarks, but they're important. You can say, well, how about smoothing this out, filtering this out, and then translating into K-tensor? No problem at all. Up to you. So if you're interested in the smoother maps, this is it. Smooth it out as you wish. Recalculate maps of K. And the other comment, well, what about comparing this with common approach when people calculate time mean eddy fluxes and estimate time mean eddy diffusivity, let's say? Well, look, because we didn't neglect time variability, we have this term. So our time mean K does not correspond to time mean F because of the extra term as well. Things are more complicated in our situation, okay? So we did not neglect temporal variability. No need for us to do this. Okay, so with all this in mind, let me go back to the flux and explain how we treat the flux before we find K. There is one more level of decision that we have to do. It's called eddy flux reduction. So the point is that the flux works on large scale through its divergence. So if flux contains rotational part, so purely solenoidal, divergence will remove it completely. It's not divergent. So solenoidal part is inert. It doesn't do any effect. It can be removed, okay, and everything will be exact. Or it can be kept in. It's removed by applying Helmholtz decomposition into velocity potential and stream function for the flux, and solving two Poisson problems separately to find F and psi. So it's all doable, it's all exact, okay? But there are two options, full flux or reduced flux. Two options will produce two different maps of K, okay? So we did both, and we did this for good reasons, because there are arguments pro and contra for following each route over here, okay? So I don't want to go into details furthermore. Now, I will base the rest of my talk on the reduced fluxes for convenience. So we have reduced fluxes, we find transport tensor K, okay? And we record all these solutions in space and time on fine grid, smooth, rough. All information is ours. We can do whatever we want with it, and no information is lost. Now, because K is tensor, any tensor can be separated in symmetric and anti-symmetric part, S and A in our case. S is diffusion tensor, this is diffusion, and A is advection tensor. Later on, you will see why one is diffusion and the other one is advection, but physically, they are fundamentally different from each other, although they both constitute K. Now, S contains three entries of information, two on the diagonal and one off diagonal. These are equal. So three information entries here, and the fourth one is there. So these three entries can be translated think about diffusion tensor as ellipse. Ellipse has two axes, major and minor, and also angle of rotation. It can be described with three variables. We do the same. We translate this in the diffusion angle and two eigenvalues. And we rank eigenvalues so that lambda 1 is always larger than lambda 2. It's our right to rank them anyway, as we wish, okay? So this A can be written as advection, but I'll get back to this later on. Now, discoveries. So we immediately have a fair number of very interesting discoveries from treatment of S-tensor. This is a random snapshot, and I'm showing snapshots of the maps of lambda 1, first eigenvalue, lambda 2, second eigenvalue. This is angle, and this is over here. This is anti-symmetric part. What do we learn from here? First of all, the eigenvalues are fundamentally polar in more than 95% of the basin and time. If lambda 1 is positive, lambda 2 is negative. We call this polar diffusion, okay? So the eigenvalues are polar, one positive, the other one is negative. Why this has been overlooked by scientists is kind of a mystery. And I have my own explanations for this. If I have extra time, I can go back to this, but that's a new information, okay? Alpha is angle, saturated red and blue indicate that this angle is not zero, very non-zero. And also everything can be animated over it. So the angle rotates. The angle rotates, all these eigenvalues change. The average between eigenvalues is also non-positive. It's half positive, half negative in different locations. This is an isotropicity, so we compare absolute values from lambda 1 and lambda 2. Saturated colors mean that the anisotropicity is very large. Okay, and A has the same values, similar values as the eigenvalues. So A cannot be neglected. Eigenvalues have to be polar. It's a completely new way, of seeing the Eddy effects through the prism of flux gradient law. And everything is in homogeneous, okay? So let me summarize things quickly over here. So first, when people treat K historically, this just historically happened, to be the standard of the field for last century probably. They always make some simplifications which we find unjustified. So first, things which are very inhomogeneous in space, and I showed this to you on slide, they are routinely estimated from Lagrangian estimates, which spread over space and over time enormously. So it means that we have really large errors in the Eulerian estimates because we use wrong information. Something has to be done about this, okay? Second, routinely, K is averaged. It can be averaged zonally, averaged in space, averaged in one spatial dimension. But if you look at the literature, there is always some kind of averaging involved. We didn't do any averaging, okay? We did not set diffusion angle to 0. And how do people do this? They neglect of diagonal terms from diffusion. So this is equivalent to saying that diffusion angle is 0. It doesn't have to be 0 at all. Diffusion doesn't have to be isotropic. We find it very anisotropic, okay? And almost routinely, except for Gent-McWilliams parameterization, the advective part is neglected. It's thrown out, and that's it. It's not even estimated. We don't even know how to estimate it, for example, from Lagrangian measurements. No one in the world knows how to do this, okay? It's one of the reasons why it's thrown out. So why can we make all these statements? Because we did a very simple thing. We took our K, simplified it according to this one level of simplification. We can throw out something, we can smooth it out, and substitute it back in the equation. So we have the equation, we have the data, we can do something with K, put it back, look at this term, and estimate errors in the equation. It's a diagnostic way of estimating instantaneous errors. Instantaneous errors are large, okay? So when we do this, we always find large, unacceptable, disallowed errors, okay? So I don't want to go into details of this, but you can say, well, so these are instantaneous errors, but do they translate in biases? So what if we keep substituting K and solving this in time, treating not diagnostically, but prognostically? So in principle, large errors can cancel each other, and they can be translated into smaller biases. Yes, this is possible option. We haven't done this. We didn't look at the biases. It's a big work to solve this and look at the biases. But maybe, well, we can keep fingers crossed and hope that they can be smaller than the errors. Okay, let me move next. Okay, so I'm checking the time. I'm doing fine. So what is the polar diffusion? Let me spend this slide and discuss the polar diffusion that we see. Polar diffusion is actually tracer filamentation process. So what the turbulence does to the tracer fields, it stretches anomalies in one direction, but squeezes in the other one. So we have positive diffusion in one and negative diffusion in the other direction. And everything changes in time. So the direction, the patches of tracer, everything changes, but it's always stretching and spreading at the same time. So diffusion and anti-diffusion coexist, okay? So this is not recognized. People call about anti-diffusion effects for active tracers, okay, such as potential reticity or momentum. But we find this for passive tracers, okay? This is a very big deal. This is a very big statement. It's a combination of diffusion and anti-diffusion for passive things, okay? So our American partners checked this in GCM solutions because one of the first criticism was, well, okay, so maybe this is QG effect. Well, in GCM, we found rather similar things, remarkably similar. So we looked at GCM solutions for North Atlantic. I don't want to go into this, it's just a separate talk. But QG results are consistent with comprehensive model results. Okay, this statement over here, let me explain it simply, okay? Without going into details of the formula. And the question is the following. Okay, we have combination of diffusive and anti-diffusive effects. But do diffusive effects win overall if we average in space, if we average in time? Do they prevail over anti-diffusive things or not? So to answer this question, we have to write down equations for tracer variance, large scale variance and small scale variance. So this pair of equations will have transfer term between them, variance transferring from small to large scales or the other way around. And look at this transfer thing, okay? If this transfer object is positive, then it's a down gradient diffusion, so the positive diffusion wins, okay? So we found globally that the effect is diffusive. And that's the only good news, actually, in my talk, because all the rest shows hidden complexity. And this is the only explicit good news simplification of the problem. So globally, things are slightly diffusive, okay? It means that if you want to parameterize eddy effects, at least to some degree, okay, at least to have some skills in the parameterization, using globally diffusive parameterization is a virtue, okay? You can't catch up all effects. You will have large errors, but at least you will win back some of the eddy effects by doing this. Okay. So the next block of questions is the following. Well, if we have negative diffusion, anti-diffusion in at least one direction, then the problem is ill-posed. Okay. So if you keep this anti-diffusion, the parameterization will blow up, definitely, after some finite time. But there are still some good news over there because things are not that bad. So first of all, this diffusion tensor rotates in time, and this rotation implies that there is some degree of cancellation between positive and negative diffusive and anti-diffusive effects. This stabilizes things. Second, negative diffusivities are always transient. They live on mesoscale eddy time, and then they go away. So there are finite time windows for the anti-diffusion to blow up the model, but most of these windows are short enough, and there is no blow up. And finally, there is also explicit diffusion, small explicit diffusion, representing sub-mesoscales in our case, and it stabilizes. So overall, even with negative diffusivity, the situation is not that bad. There are some actors playing against the negative diffusivity problem. Okay, that's enough about diffusive part. Let me talk about advection part. So from here, let me just skip some things and focus on this. So the statement is quite simple, and for those of you who don't know this, just trust me. So the A part, the antisymmetric part of the transport tensor, can be translated exactly into advective term with this advective flux. So there is one-to-one exact translation of it into advection term, not diffusion term, but advection term. And in this advection term, there is advective flux, and there is velocity acting on this advection. And this velocity is non-divergent, and it has stream function, and this stream function is A. So to put it in simple description, A, which is the last entry of the K tensor, and that's the entry that goes into asymmetric part, antisymmetric part. A is velocity stream function. So A has velocity, and this velocity we call eddy-induced velocity. So it's a fundamental object. It's part of K tensor. Okay. Let me skip these statements and just say, well, look. So A is stream function. So velocity is in terms of derivatives. So A must be fundamentally inhomogeneous in space. There is no way to estimate A as a constant in space object because all its action will be lost by doing this. It's completely inhomogeneous. And this is opposite to treatment of diffusivity and diffusion part. They can be homogeneous in space and still act. This one cannot. Now, since we started to talk about advective part of the K tensor, the first and big thing that should come in mind, at least it always comes in mind of people who work with parameterizations, eddy parameterizations, is what is the connection between our eddy-induced velocity and Gent-McWilliams parameterization? Because GM parameterization, probably most famous parameterization for oceanic eddies, GM parameterization also has concept of eddy-induced velocity, different velocity. They call it bolus velocity. So what's the difference between our eddy-induced velocity and classical GM bolus velocity? That's a big question. And this is when Jim McWilliams joined our project, and we published 2 papers on this. And here in one slide, I'm going to give you crash course information on that comparison between us and GM. So here it is. This is our approach. In our approach, we estimate K tensor. Nothing is neglected, no constraints at all. So it's a free brute force estimate. And then K-tensor falls apart in the S part, here it is, and A part. A part is translated in that advection, A is translated in this velocity. So here it is, we do nothing extra, only estimate K. In GM approach, the bottom line is that there are two constraints. So in our case, it's zero constraints. In GM case, there are two constraints that they do. So first constraint is that they say, well, this velocity we want to take as bolus velocity. What is bolus velocity? Bolus velocity is hidden mass flux due to correlations between isopycnal thickness fluctuations and velocity fluctuations. So it's a Stokes drift for fluid dynamicists of certain type. So they take this bolus velocity and fit it in, okay? So look, we didn't do this. It was all natural for us. So after they fitted bolus velocity in, they sort out this equation, put all the other terms involving primes on the right-hand side, and fit this with isotropic positive diffusivity. Isotropic and positive diffusivity, okay? So first there is constraint here, and second there is constraint in that field. And this is called GM approach, most famous parameterization. So the immediate question that comes to mind, and this is what we worked out, is how different is this velocity from that velocity, okay? So for our solution, this difference is more than order of magnitude. It's 40 to 50 times. Our velocity is 40 to 50 times larger than this one, okay? And there are good reasons for this, because the physics built in is different. And the question was, okay, so maybe this is QG effect. What about North Atlantic Comprehensive Model? Again, so our American part of the team did the North Atlantic calculations, and they got somewhat smaller coefficient. From 40 to 50, it was reduced to 20 to 30, probably by a factor of 2. But it was still more than order of magnitude, okay? So the bottom line is that our approach, which has no constraints at all, okay, produces different, fundamentally different description from GM. And this has to be counted somehow, okay? So our Eddy-Induced velocity is persistently much larger than bolus velocity, more than order of magnitude. So Jim was convinced in this completely. He is a co-author on 2 our papers on this subject. So let me move on. And okay, I'm running out of time. Aviv, how much time do I have left?
It's maybe 10 more minutes. It's formally until 1/4 to the hour, but we can go
on. Okay, so 5 minutes is okay?
Yes, absolutely.
Okay, so I want to show one slide, but I don't have time to explain it in detail. And this slide is about the following. Since we have many pairs of tracers, we have many maps of K-tensor for exactly the same velocity field. How different are those Ks, okay? So we did a rather tricky analysis of figuring out whether Ks are different or not. Just look at these two panels, and I'm pretty sure that your eye will tell you that this map is different from that map, okay, visually, okay? And it's just the same snapshot of full field, same turbulence, same thing, just one component of K from two different pairs. So the bottom line here is the K-tensor is non-unique, okay? If needed, I can go back to this slide later on, but the non-uniqueness of K is really headache. We don't know what to do about this. We have ideas, but even discussing these ideas will take really big time. So I don't have time to do that. But keep in mind, our conclusion, solid conclusion, based on a GFM publication, that case fundamentally non-unique. Now, quick summary of the results. So first, for the diffusive part, we found polar diffusion. It means that positive and negative diffusivities always coexist. Okay, it's a fundamental and robust statement. So they imply eddy-induced filamentation, and it's physically different from classical view of diffusion, how eddy effects were viewed forever. Okay. The negative diffusivity on the one hand is a really big problem. On the other hand, it has mitigating circumstances. Negative eigenvalues are transient, there is rotation of diffusion angle, there is explicit diffusion. So there are things to discuss. Third, overall, variance is transferred downscale, which means that overall diffusive effects win. They win slightly, but they win over anti-diffusive effects. Next block is about A-tensor. So first, it has to be taken into account. It's large. Diffusion alone is fundamentally insufficient to describe eddy effects. A has to be brought into the picture. And only small fraction of A can be explained by bolus velocity in GM way. So GM missed 90% of the story about A. So something has to be done. Then there is an issue of non-uniqueness of transport tensor, but I didn't have time to talk about this. I just outlined this problem for you. And big consequences of that is that probably we have to rethink the whole flux gradient relation. It's either incomplete and we have to extend it, or maybe we have to abandon it after 100 years of messing with it, abandon it completely and treat it as stochastic. But something needs to be done. It's a fundamental thing. I didn't talk about PDFs of various things. Let me skip this and move to some afterthoughts and further extensions. This is my last slide. This is really last slide. So what's the key aspect of our work? What's the main message? So for those of you who didn't like it or want to get one message back, here is the one message. For the first time, okay, in science, at least in ocean eddy modeling, we imposed no constraints on K. No at all, okay? And this provided us with really massive information output that we sorted out. So imposing no constraints is the key to understand our work, okay? And then we raised several big questions from our analysis. Several big questions came out. So what should we do about flux gradient relation, okay? So we have indications, some indications that the problem is there on the most fundamental level. Second, maybe we should completely forget about fluxes and talk about eddy flux divergences and model eddy flux divergences. This is something even more fundamental because until now, people talk about eddy fluxes, not divergences, okay? Because divergences enter as the final eddy effects. Maybe we should come up with relations for divergences and redo everything from that perspective. And finally, from what we found from the level of complexity, we predict that finding closures for turbulent effects will be difficult, more difficult than people thought. And maybe we should reconsider this approach and use it in a weak sense. Do not even try to reproduce all eddy effects, but single out and reproduce maybe half of the eddy effects, but in some robust way, okay? And then there are further extensions to our work. We keep moving along few lines in this list, but the list is huge, and there is a huge scope for further research. So on this point, I want to thank the audience Thank you for inviting me. Thank you for giving me this opportunity, and I'm looking forward to answer your questions and be grilled by the audience. And I can also clarify some things which were not clear because I moved quickly through the material. Thank you.
Thank you very much, Pavel. I was thrilled to my seat in the entire talk. Very interesting. I have a lot of questions, but let's open it to the audience. I see that Nathan has unmuted himself. Nathan, would you like to ask a question?
Yeah, sure.
Thank you, Pavel. It's a very full and thought-provoking talk. So over the year, I'm not an expert on the solutions that you are so meticulously work on, but over the years, I've heard a lot of theoreticians discuss various elements of K-theory, and I don't ever remember seeing that kind of result. What's new in your approach?
So the key new thing was, Nathan, that we found the K without no constraints. The second key thing is that we systematically explored. So without no constraints, it's a new object. It has been never studied and explored without constraints. There are always constraints. Okay, so it's a new object for us. And then we systematically sorted out this object: diffusive part, advective part, non-uniqueness, other things.
So do you get these results because you split it into the symmetric and anti-symmetric parts of the tensors?
No, nothing. This is not novel. This is not novel. People split it.
So where is the how should I say it? The core of novelty in what you are describing.
Okay, let me explain it in different words. So we have no constraints. So let me list constraints that people made. Okay, so there are different approaches. One very common constraint is to use averaging of some sort, to average K in space, for example, to average K zonally, if we talk about atmosphere and zonal solutions, to average K in time. So different families of different spatial temporal averagings. It's one block of constraints. The second block of constraints, and for example, Baylor, Fox-Kemper, and Scott Bachman, and this big US team, they do this routinely. When they estimate K, and they estimate K by regression, okay? So regression is already constrained because it's not exact, it's regressed. But they do something else. On the top of regression, they put second constraint. The second constraint is that they say, well, our K must have both eigenvalues positive. Okay? So it means that they, by construction of their estimate, they disallow any negative eigenvalues. So they get the object, but it's regressed and it's positive by construction. So these are three constraints: averagings, regression, and positiveness.
Positiveness.
Yeah. Okay. So three classical. There are other smaller constraints, and we have nothing of this. Nothing of those.
That's impressive.
Yeah.
Is it expensive computationally? What prevented people from doing it until now?
Well, it's moderately expensive computationally. So what you need is, I don't know, probably a dozen of processors available, not even 100. Okay, so it's a medium-sized computation. Okay, but you ask a very good question: what prevented people from doing this? I think there is a tradition, going to our fathers, my fathers and grandfathers in science, tradition of averaging before calculating K. I don't know. This is ingrained in people. And second, there is a fear there is a built-in fear of negative diffusivities. There are many papers that show something negative in the diffusivity, and then they abruptly stop and say, okay, we don't know what to do next. We just report this result, and that's it. So many people touched on this, but they never went further. So it's
what you're saying,
built-in fear.
what you're saying, the obstacle was the concept of negative diffusivity, right?
Yeah.
I came across it personally. Like I remember I saw somebody present the results and they were like, oh, but we find negative diffusion. So instead of it, we do something and ask, but what's the problem that you have negative diffusion? Why do you just abandon it? Well, it's bad. It's negative. It's negative diffusion. That was just this. And I guess the implication is that it causes unstable numerics often, but from that it went on, it seems, to kind of be categorically bad somehow, just conceptually, perhaps.
Interesting.
It's conceptual stumbling block. Negative diffusivity, that's it. We have to stall, park our car, that's it. The journey is over.
Pavel, I wanted to ask, there were all these terms on the right-hand side of your initial equation, like temporal derivative of the C prime, that you said, oh, we're lumping this in we're assuming it's the divergence of some field, or the gradient of some divergence field, I'm sorry. And what happened to those? And why did you assume that? And can you say something about those?
Well, okay, so you were asking about this object.
Those on the right-hand side. Right?
Yeah. So look, in order to apply flux gradient relation, and flux gradient relation is the most fundamental point in my story. There is nothing before it. That's the foundation. In order to do this, we have to have fluxes. This is flux because it's vector, and this is divergence of flux.
Yeah,
but this part is not flux. So it's part of the eddy effect, which is not flux. So either we treat it separately, or for example, just put it aside and don't worry about it, or we translate it in some extra flux. So we opted out to translate it in the flux. And we did this by saying that, well, it's a divergence of unknown flux. Let's find this flux. So we followed this route because we wanted all eddy effects to be translated in K, okay? Not part of the eddy effect. This is the biggest part. So 90% of eddy effects is here, and 10% is there, roughly speaking, okay? Mm-hmm. But to be honest, we did both. So we also translated in K only that part. And even more, I didn't have time to talk about this. We translated into K-tensor components each of these three guys, because they're all separate over here. So we can make three maps, 1, 2, 3, and the fourth map for that one, okay? So we played this over completely, okay? All combinations, all elements, and it's just for the sake of brevity, I'm giving you like the main punchline. So I decided to talk about joint flux. Okay. Follow the papers. This talk based on 6 or 7 papers. So it's overview. It's overview rather than a single talk.
Great.
You mentioned earlier.
Sorry.
You mentioned earlier that somehow you will focus on QG. Did I hear it? Do I remember correctly? In some earlier part of your talk?
Yes,
what will happen if you extend it to shallow water? It won't change much. I mean, it doesn't have to be the Laplacian that relates the divergence to the stream function, I guess.
So yeah, thank you, Nathan. This is really good question. So all my talk, everything in my talk was on QG. Only 2 times within my talk I mentioned that American team, it's Igor Kamenkovich and his PhD student, Yu Yang Lu. So they were part of our project and they worked with comprehensive North Atlantic model. They worked with high-com data and did essentially the same thing, okay? I just cannot put this in my talk because they have their separate own talk, okay? I'm talking about QG and basics. They talk about like serious ocean model for big guys. They found essentially same thing. Okay. In terms of eddy-induced velocities, they found velocities which are about twice smaller than ours. They still order of magnitude bigger than GM velocity, bolus velocity, but not that bigger. And in terms of polar diffusion, they found exactly the same. So 95% of the domain is polar diffusion, okay? And they also worked with similar objects, but in primitive equations. So they had to sort this into extra fluxes by actually solving global Helmholtz decomposition problem. It's a big mess. They were solving Poisson problem, but iteratively, not directly as us, okay? And they worked with this, yeah. And they couldn't, another issue is that we had a lot more tracers in the ensemble. And we had more than a dozen routinely, so it's 100 pairs. And they could afford, I believe, 2 or 3. I think only 2. Because it's just expensive. It's just very expensive.
No,
maybe we can open it for other people to ask questions. If anybody's has additional questions.
Yeah, I have. So Nathan started by saying he's not an expert, but in my case, it's really true. So perhaps I'm asking a stupid question, but so is it all relevant for horizontal mixing? So I'm trying to understand whether it would have any consequences for vertical mixing as well and carbon storage and stuff like that.
Thank you, guys. This is a very good question. So in this talk, we treated things simply. So all cases are purely isopycnal, long layers, nothing vertical, nothing diapycnal, just by construction. Okay. So our American collaborators, they tried to look at the vertical direction. They arrived at some conclusions, but the conclusions were not sufficient for publications. Okay, so basically we made some attempts, not me, not my group, their group, and no interesting results so far. But it's completely open problem, and adding third dimension and treating case 3x3 tensor is absolutely valid and useful future research direction to be done.
Right. Anybody else? Well,
yeah, I'm already past the hour, so
yeah.
Really great. Thank you very much.
Pavel, you are welcome to have beer with us.
Virtual beer. Thank you, Nathan.
Okay.
Thank you all for inviting me. Thank you for asking questions. It's a great opportunity. And well.
And thank you for presenting your results.
This was fascinating, extremely thorough, very important. And I have about 6 papers to read now. Subject. So I'd go on another hour and talk to you, but I guess I should come to the UK soon enough.
Well, and I hope to see you guys soon.
Thank you, Pavel. And next time, hopefully in person in Israel.
Thank you.
Yeah. Okay. All right. All the best.
Thanks, everyone.
Thank you. Bye-bye.